All right, hello class. Today we're going to be looking at integration by parts. And this is our first jump into actually learning truly brand new techniques. So if U substitution is basically a reverse chain rule, okay, then by parts is essentially a reverse. I probably should have written reverse up here. By parts is a reverse product rule. Okay, so let's take a look at how we might want to do that. All right, so let's start with our regular product rule. So let's say I'm differentiating with respect to x a function, say u of x, times another function g of x. Okay, so from the product rule we know, all right, that'll be the derivative of the first, say u prime, times the second left alone, plus now the first left alone, so just u of x, times now the derivative of the second. So there is our normal product rule. Now you might be wondering why I'm using u's and v's, and that's, well, that comes from basically how the by parts formula is typically represented using u's and v's. Okay, but we could have done f and g, however we want to do this. But you might think, well, to reverse this, all we need to do is basically drop the derivative thing here and put an integral thing here, and we would have it. So you might think that, all right, all we need to do now is just say that the integral of u prime of x v of x plus u of x v prime of x all dx is equal to u of x times v of x plus c. And this is true. Okay, that is not arguable. You can reverse things like this, but the issue is that we won't often see things in this perfect setup, right? It's very rare that you will see something this nice. Those of you going on to differential equations, you might find yourself in situations where you make this happen. Okay, but often what we see instead is an integral with just two pieces. So we'll often instead, let me do it over here, say in red, we would see something like this, maybe x sine x, okay, dx, right? It's very rare that we would see something as nice as like 2x sine x plus, say, x squared cosine x dx, okay? Very rare we might see something like this. Okay, so if you look closely at that, you'll see that this is a product rule result, right? But again, this is really limiting. Okay, so we want to try and advance this a little bit. So what we're going to do is actually split up this integral. So we can say, all right, let's just look at the integral of u prime of x times v of x dx plus the integral of u of x times v prime of x dx, and that'll still be equal to u of x times v of x plus c. Okay, and then now what we're going to do is move one of these guys over. So I'm going to take this piece and move it over. Okay, so that we'll have the integral of u of x times v prime of x dx is equal to u of x times v of x minus the integral of u prime of x v of x dx, and then we'll need to sneak a plus c in there. And this is essentially our by parts formula. Okay, if we have a integral with a product, okay, what we need is we need a piece that we can differentiate. So that's this. And we need a piece that we can integrate. So we need a u to differentiate. So I'll just put diff. And then we need a v prime to integrate. Okay, I'll just put int. And then we are going to put it into this formula. All right, now this is how integration by parts is usually written. It's usually written as the integral of u dv is equal to uv minus the integral of v du. Now, what's going on here is basically they're dropping all the x stuff just to make this simpler to figure out, but the u is just u of x, okay, and dv is actually v prime of x dx. You can think of it that way, all right, the thing that you can integrate. And uv, of course, stays that way. And here, the v is just v of x, while the du is u prime of x dx. Okay, but we just, there's definitely more to it if you want to be very strict, very rigorous about what you're doing. But I think of it as we just write it this way so it's easier to deal with. It's more compact. Okay, so always with by parts, you need to choose a u, and this u needs to be easy to differentiate. Okay, I'll just put easy to diff. And hopefully reduces, i.e. becomes similar, or simpler. Okay, so when we have that, once we choose a u that works that way, then dv is everything left over. So everything that's left. Okay, so that is the key. Once you find u and dv, it all just sort of follows from there. It's all about picking the right values, though. All right, so if we just look at an example, let's say the integral of 2x sine of x dx. Remember, this is a by parts. So what you're really looking for is always your first goal is, well, let me try u substitution. And if that doesn't work, then we're going to try something else. And a u substitution, whether we let u be, say, sine or 2x or whatever we try with the u substitution, it's just not going to, it's not going to happen. Nothing's going to happen here. Okay? So we might think by parts because we have two things multiplied together. So whenever, it's sort of what you're looking for with product rule. So we have two functions multiplied together, and you'll notice there's no like stuff. It's not like sine of stuff. So, and no, I'll say internal stuff that would make us think chain rule or u substitution. So that's going to make me think. Okay, so I'll just say this makes me think by parts. Okay, and the reason for that is I can pick something that's differentiable and easy to differentiate and simplifies when we do it. So here, my 2x, this is easy to differentiate and simplifies when it does. Okay. Then what's left over, this sine of x dx, this can be integrated, right? This is integrable. And it's not too hard to integrate. But the reason we didn't want to choose, like, yes, sine is easy to differentiate, right? However, it doesn't simplify, okay? When we differentiate it, we get cosine. And if we were to differentiate it again, we'd get negative sine, and then negative cosine, and then back to sine again. So it doesn't simplify if we wanted to differentiate. Well, 2x does. Okay, there's a little more to finding your u than just that. Okay, we'll talk about that when we get there. So I'm going to choose our u to be 2x, and you could bring the 2 along with this, you could bring it along with sine. The constants aren't really going to change things that much. And that makes du, well, now we just differentiate this. That'll be 2 dx. So I'm doing this just like we did back with u substitution. However, we have another part now, and that is dv. dv is everything that's left, so that'll be sine x dx. So v, now we're integrating, okay? We're integrating to get from dv to v. All right, so the integral of sine is negative cosine x. Okay, because if I differentiate cosine, I would get negative sine, so I need another negative there. Notice we're not throwing in a plus c here. This is just, just our work. So, our integral that we have up here, let me work it here. Well, our by parts formula is uv minus the integral of v du. Okay, if you write it every time you work on this, you will, get it stuck in your head, right? So u is 2x. Cool, put that in. I'm going to be really explicit here with parentheses and stuff. You don't have to do this. I'm just being extra careful. Then v. So v here is the negative cosine x. Okay, then it'll be minus the integral of v, so that was minus cosine x, du. Well, du is just 2 dx. Okay, and we can put that in parentheses too. All right, so if we simplify this down a little bit, we're going to get negative 2x cosine x. Okay, and then this minus and this minus will cancel out to give us a plus the integral of 2 cosine x dx. And now we've actually reduced this down to something that we can integrate. Okay, so it'd be negative 2x cosine x. Then plus, well, the integral of cosine is sine. And I'll throw in the plus c. I usually throw in the plus c at the very end there, just because we have an integral still left in this step. So we could put it, we could leave it till later, There we go. Okay, so maybe we should actually check to see that if we differentiate this, we would actually get back to what we started with. Okay, so if I'll do that in green. if we differentiate our result here, negative 2x cosine x plus 2 sine x, I'll throw in the plus c2 because that'll just be 0. Well, the derivative of this piece, this negative 2x cosine x, that of course is going to be a product rule. So it'll be the derivative of the first, which is just negative 2, times the second function left alone, then minus, it's really plus, but since we have a minus there, it'll be minus 2x, so leaving the first function alone, then the derivative of the second, which will be negative sine x. Okay, then it'll be the derivative of this, so 2 sine x will get plus 2 cosine x. Okay, and the derivative of a constant, of course, is 0. Well, we get negative 2 cosine, actually, I'll just go ahead and say, check that out, negative 2 cosine, those guys cancel. And this negative 2x, negative sine x becomes 2x sine x, which is what we started with up here. Okay, so this method actually does work, and it turns out the second you find the right u, you're good to go. All right, so here's another example, and it's possible that one integration by parts will not be enough. So the reason I think by parts here, okay, we have the multiplication of two things, an x squared and an e to the 5x, but this can't be a u substitution because usually you would let this stuff be your u for a u substitution. In this case, though, it wouldn't work out because if you let u be 5x, du would be 5 dx, and that wouldn't work. If this was, say, 5x cubed, right, if there was a cubed here, and then you could say that's 15x squared, then you would have a u substitution. Since we don't have that, it's not going to be a u substitution. And since it's just two things multiplied together like this, one of the, actually they're both easy to differentiate, both easy to integrate. However, I'm going to let our u be this x squared because it's easy to differentiate and it will simplify when we do that. Whereas here, we'll let this be the dv. And once you have it, that's the work, really, because now we just say, all right, we're going to let u be x squared. So du is going to be 2x dx. And then dv is all the stuff left over, so that will be e to the 5x dx. Now we're going to integrate this. So remember, the rule is something that's not too complicated to integrate. Okay, so it doesn't need to get simpler when we integrate it. It just needs to be able to be integrated. All right, so if dv is e to the 5x dx, then v is 1/5 e to the 5x. Now, we're just going to write out our rule. It'll be by parts, it's uv minus the integral of v du. All right, so let's fill this stuff in. U is x squared. V is 1/5 e to the 5x. Okay, minus the integral of v du. Okay, so du is 2x dx. All right, so let's simplify this out a little bit. This will be, I'm going to move that 1/5 outside. 1/5 x squared e to the 5x, okay, minus the integral of, if we sort of simplify this down, it'll be 2/5 x e to the 5x dx. Okay, now we're not done. This is going to be another by parts, because we can't set up a u substitution for the same reason I described before. It's because we would still have an x there. But once again, we can choose, I'll choose this whole thing as our u, since not much easier to differentiate than 2/5 x. Now, yes, e is very easy to differentiate, but it doesn't simplify when we do it. So we're going to choose that as our dv. Here, though, since we're moving down to new letters, let's call these u1 and dv1. All right, you could put bars over them. You could use different letters, whatever you want to do. So our u1 will be 2/5 x. So du1, okay, will just be 2/5 dx. Then over here, our dv1 is going to be e to the 5x. Oh, actually, it's the same as we had up here, right? So we could actually use that work we've already done. We don't have to do it again. But I'll go ahead and do so. Sorry, that would be v1. Okay, now here's where we need to be careful, because in our answer, I have 1/5 x squared e to the 5x minus this whole integral. Well, this whole integral is going to be u1 v1 minus the integral of v1 du1. Okay, so we need to put that in parentheses here, because we are dealing with this whole integral here. All right, so we will be distributing that negative across. So I like to go ahead and do that here, but that's one of the nice things about math, is as long as you do it. So if we distribute that, that'll be minus u1 v1 plus the integral of v1 du1. Okay, so now I'll start plugging this stuff in. I'll leave that 1/5 x squared e to the 5x. Okay, then minus u1 v1. So u1 is 2/5 x, and v1 is 1/5 e to the 5x. Okay, then the integral of v1, so that was 1/5 e to the 5x, and then du1, so that would be, I didn't put my, oh, there it is, sorry, 2/5 dx. Okay, and we are almost done. Let me simplify this. 1/5 x squared e to the 5x minus, when we simplify this all together, we'll get 2/25 x e to the 5x plus, and then this will be the integral of 2/25 e to the 5x dx, and this is just, say, a Cal 1 integral. We can integrate that now. Let's go ahead and do that. 1/5 x squared e to the 5x minus 2/25 x e to the 5x. And then when we integrate this, this is, of course, 1/5 e to the 5x again. So we'll end up with 2/125 e to the 5x plus c. And there we go. All right, now that might seem like a lot of work, and there's quite a bit to this. And in fact, if we had started with an x cubed, we would have had to do another by parts. And if there was an x to the 4th and even another by parts. So there is a trick, okay, that we can use to actually help us speed this up, but it will not work all the time. So let's take a look at this trick that can help us. Okay, so here's how the trick works. I want to basically give you this caveat that it only works when the u that we're going to be choosing for u substitution is a nice function whose derivatives eventually go to 0. Now you might think, well, hasn't that been all of the situations? And so far, yes, but not always. So, for this example, how we would do it, okay, is we would set up a table, and I like to mark it as D and I. Okay, D for derivatives, I for integrals. You don't actually have to write that part, but while you're learning. And then in the D column, I picked the thing that I would have normally let be my u. So here, x squared. Okay, then in the E column, I pick the thing that I would normally let be dv. So you can think of this as the u and the dv piece. Okay, then in this column, we start differentiating. So I start with the x squared, then 2x, then 2, then 0. Right? And this is what we need to get this to work. There are ways that you can extend this, but at that point, I think it's just easier to use normal u substitution. Then here we start integrating. So it'll be 1/5 e to the 5x, 1/25 e to the 5x, and 1 over 125 e to the 5x. And we can actually keep going, but you could stop, and I'll show you why. Now, one thing about u substitution, remember, is it goes from plus, minus, plus, minus. So how you join these together, right? Ignore this piece, but we do diagonals. And then we alternate with a plus, minus, plus, minus, but here we're going to be multiplying across here. So that's why we don't have to go any further past the 0, because it will just zero it out. So when we go to do the integral, now it's just this piece times this piece, so that will be, all right, is x squared over 5 e to the 5x. Then this piece times this piece, but we throw in a minus, so it's minus the 2x over 25 e to the 5x. There'll be plus these two, plus 2 over 125 e to the 5x. Then 0 times whatever we got here would still be 0, so we're done. So that's why we need it to zero out, essentially, is eventually we need this table to end. Okay, there are cases where this is not going to work. All right, so let's do another one real quick of a situation like this, and then I'll show you some examples of where it won't work. All right, for example, here we have 2x cubed cosine of 3x dx. This is going to be a by parts, because like before, if this was, say, a 3x to the 4th, this would be a version of the derivative of the stuff inside here, so we could actually do a u substitution. In this case, we can't, so this will be by parts, since it's just two things multiplied together, and we have something here that not only simplifies when we differentiate, but actually eventually disappears. So 2x cubed, as we differentiate, so our first derivative will give us 6x squared, our next derivative will give us 12x, then we'll get down to 12, then 0. It eventually zeroes out completely. Okay? So now what's left is our cosine of 3x, and we're going to start integrating this basically until here. We don't have to go any further just because we'll be multiplying by 0, right? So integral of cosine of 3x is 1/3 sine of 3x. Remember, we're integrating here, so the plus and minus signs go opposite than what you're probably used to with the derivatives. All right, then we'll get 1/9 cosine of 3x, and since we're integrating, this needs to be a negative. Okay, then we'll get a negative 1/27th sine of 3x. Let's make my table look a little nicer here. Okay, then we integrate again. The integral of sine of 3x is going to be a negative, but now that we have a negative, we're going to get 1/81 cosine of 3x. Okay, so now we go through and we do our multiplications diagonally, just making sure we alternate plus, minus. I don't know if you can see that. Plus, minus. Plus, minus, plus, minus. Okay, so it'll be 2x cubed times this thing here, the 1/3 sine. So I'm going to say that's 2/3 x cubed sine of 3x. Okay, here it will be minus, but I have a minus here, so minus and minus, it will be a plus 6/9. So that will be, I'll just write it as 6/9 for right now. Okay, and then I will, now that I've just done it rotely, 6/9, that'll be a 2/3. Okay, so we've done this piece. Now it will be this 12x times 1/27 sine 3x. A plus here, minus there, so we'll keep that minus. Get 12/27 sine of 3x. Sorry, that would be a 12. I still have an x there. Okay, and then that 12/27, we can take 3's out of both of those. So we take a 3 out of here and get 4. We take a 3 out of here and get 9. Okay, and then this last piece we introduce a minus, and so it'll be minus 12/81 cosine of 3x. And just like before, we can take 3's out of both of these and get 4/27. Okay, plus c, and there we go. That has sped up our by parts tremendously. Okay, however, it's not going to work for everything. Okay, so let's talk about the cases where it's not going to work. Here's an example where that table method that we just discussed is not going to work for us. Okay, so this integral here, I think is, it's set up in such a way that, yeah, okay, by parts makes sense, right? I have an x squared times an ln x. However, in this case, we are not going to choose x squared as our u, right? Which is kind of flies in the face of what we've been doing so far. But that's because, remember what we need for our u. Our u needs to be differentiable, all right? So I'll say it's got to be differentiable. So I'll say diffable. And it simplifies when we do so. Okay, it doesn't have to go to 0. That's what we need for the table method, right? It needs to go to 0, but that's not an actual requirement for normal by parts. And we need what's left over, dv, needs to be fairly easy to integrate. Okay, and in this case, if we were to choose x squared as our u, choosing dv to be ln doesn't do that. ln is not fairly easy to integrate. In fact, so far, in our progress of this course, we don't have an integral rule for ln. Okay. No ln x rule yet. So that's why we want to choose u to be ln, to be ln x, because it differentiates and it simplifies. 1 over x may not seem super simplified, however, that's better than ln x, right? Like way better. And then dv ends up being what's left over, which is the x squared dx. So v is 1/3 x cubed. So let me write our uv minus the integral of v du over here and fill our pieces in. So we'll get uv, so 1/3 x cubed times the natural log of x minus the integral of v, which is 1/3 x cubed v du. So 1 over x dx. And so what we're really trying to do is not just find something that simplifies, your u or v or whatever, but also simplifies this final integral that we have to deal with. So here it does, because this 1 over x cancels and leaves us with just 1/3 x cubed ln x minus the integral of 1/3 x squared dx. And now this is just a power rule, so we'll crank that out, leave this first part alone, and so this will be minus, here we'll get another 1/3 x cubed, so we'll get minus 1/9 x cubed plus c, and there we go. So it actually turns out that there's what I like to call a hierarchy of u's when choosing u for by parts. Typically, you would choose, say, x to a power in most cases. Okay, so your x's, your x squared, stuff like that. But what you would choose ahead of that, okay, I'll put it over here like this, your ln x's, or any inverse trig function, you would want to choose ahead of an x to a power, and then very rarely would you choose an e to the x or a normal trig function, because these are your repeaters, right? So you usually don't want to choose your repeaters because they never, they never settle down, whereas these are the ones that go to 0 if you differentiate them enough, and these just simplify once and that should be enough, provided the problem's right. All right, so these simplify once and that should hopefully be enough. Okay, so if you ever see an ln or an inverse trig in your integral and it looks like it should be by parts, you're going to choose the ln or the inverse trig. All right, that's the way you're going to want to do it. If you don't, and all you have are like powers of x and like e to the x, always choose the power of x, because that'll go to 0. You can use your table method, right? Because this we could set up as a table and go down to the 0. Whereas here, repeaters, you might not think you would ever choose these. However, there are cases where you would. So let's look at a case where we would choose a repeater. Okay, so here's an example of an integral where all we have are things that repeat. So whatever you would choose to be your u is always just going to repeat over and over and over again. For example, e to the 2x, well, its derivative and its integral will always have a form of e to the 2x in it. Cosine of 5x, well, no matter what we do, integrate or differentiate, we're going to be cycling back and forth between sine and cosine over and over and over and over again. So when you have only repeaters, let me show you what you do. Okay, so it's going to seem like all is lost, but I like to set a u So just do the e to the 2x as your u. It's not really going to matter that much. And we'll just always use this as our u and our du. Okay, so we're only going to do that work once for our u. Our v, on the other hand, we're going to let change. So when we do this, our dv, and I'm going to call it dv1 because we're going to actually have to do a standard by parts here. So we'll say that's cosine of 5x dx. So then v1 is going to be, remember we're integrating here, so it'll be 1/5 sine of 5x. All right, so we're going to do our usual by parts. I'm just writing it here so we remember it. So this will be uv, so e to the 2x times 1/5 sine of 5x minus the integral of v du. So v, our 1/5 sine of 5x, and our du is 2e to the 2x dx. Okay, so now we have this new integral, but I'm going to pick u to be the same thing again, right? I'm just going to keep that as my u and just change my v. So now I have a dv2, and that's going to be everything that's left over here. So that would be 2/5 sine of 5x. Okay, dx. And when we integrate that, well, now we're going to introduce a negative, so it'd be negative 2/25. Remember, you divide by that 5, cosine of x, or 5x, excuse me. And now, we're going to put in our by parts formula in this set of parentheses, right? So it will be u, v, so e to the 2x, times negative 2/25 cosine of 5x. Now the biggest problem I see with things like this is getting the signs mixed up. Okay, then minus the integral of v. In this case, that'll be negative 2/25 cosine of 5x times du. So that'll be 2e to the 2x dx. Oh boy. Okay. So let me simplify this a little bit. It's going to look awful, okay? But we're getting there. All right, so this part I won't change, and then we will distribute this negative sign. So we already have a negative sign here, so that will make this thing positive. So it'll be plus 2/25 e to the 2x cosine of 5x. Okay, now we already have two negative signs here, so that'll make that positive, but then we bring in this next one and it'll make it negative again. So it'll be negative the integral of 2, actually, sorry, that will be 4/25 e to the 2x cosine of 5x dx. Now, here's the trick. You might think, well, hang on, we just got right back to where we started. This is just going to continue to repeat forever and ever and ever. However, notice we have this constant sitting out front. Okay? So if I were to rewrite this integral, if I just called it I, capital I, okay? And then I rewrote this as, let's take that 4/25 out and had it multiplied by I. Okay. So what we have here, forget about how awful this looks. Just think about this as we now have an equation, I, with a bunch of junk, minus 4/25 I. If I asked you to solve for I, well, how would you go about it? You'd probably move this over and simplify the like term, so you get I plus 4/25 I is equal to this stuff here. Okay, I'm just going to write this stuff. Okay, just to simplify life for us, just for a bit. I'll get back to it in a second, but I don't want to write it over and over again. Now, 4/25 I, 1 I have a 1 sitting out here, that's 25/25. So if I bring these together, or you can just factor out the I, and you still will be adding this. So you'll get 25/25 plus 4/25 I here is equal to this stuff. Okay. And so you will get I times, now when we make this, we actually do the arithmetic here. We're going to get I times 29/25, and we're going to move that over to the other side by multiplying by the reciprocal. So I is actually 25/29 times all the stuff we were looking at here. Well, I, remember, was just our integral up here that we started with. So this tells me that our integral, which was e to the 2x cosine 5x dx, is just this weird constant, 25/29, times the stuff we got from our by part stuff. So our stuff was 1/5 e to the 2x sine of 5x plus 2/25 e to the 2x cosine of 5x. Throw in a plus c if you've got the room. And there you go. That's how you use by parts when you have two repeaters. Okay, and when you have two things that always repeat, yes, you do get back to what you started with. However, then you can just solve, provided you have some sort of constant or thing going on here. All right, now there is one last technique I'd like to show you with by parts. Okay, and that's something like this. This would work for ln and other situations too, but in this situation, we see that we have just one function. So you might not think by parts would actually work, but actually we can use by parts here. Okay, may seem kind of crazy, but remember, all we need is something that can differentiate and get a little simpler when we do. All right, that's sine inverse. And we need everything else. Well, our everything else would be dx. And actually, you can think of there being a 1 dx there. Okay, so yeah, we're going to let u be sine inverse of x, making du equal to 1 over the square root of 1 minus x squared dx. Okay, then our dv I'm going to let just be 1 dx, making v x. Right? When you integrate 1, you get x. Okay, so when we do our uv minus the integral of v du stuff, we're going to get uv, so that will be x sine inverse of x minus the integral of now v du. Well, v du, that's going to be x times 1 over the square root of 1 minus x squared dx. And this, it might not seem much simpler, however, this is a u substitution. you can let u be everything that's in the denominator here, say 1 minus x squared, because then du is negative 2x dx. Now, I might not have the negative 2, but we've got the x dx. All right, so negative 1/2 du is x dx. Okay, so our new integral, okay, becomes, you write it in this blue, so it's going to be 1 over the square root of u times negative 1/2 du. All right, so it does get a little tedious having to rewrite all this stuff over and over and over again. I'm going to, since I have a negative and a negative, I'll just make that a plus. I'll take the 1/2 outside, and I'm going to rewrite this as u to the negative 1/2 du. Okay. Then the 1/2 will come along for the ride. This will be u to the 1/2 over 1/2. Now when you divide by 1/2, that's the same as multiplying by the reciprocal, so that's the same thing as multiplying by 2. You can also think, oh, I have 1/2 and I'm dividing by 1/2, so those guys just cancel out nicely. So let me throw in the plus c now. And all we've got to do here, again, we write this down, and we just need to put the x's back in. So our u, I probably should have used a different letter here now that I'm thinking about it. Sorry about that. Hopefully it wasn't too confusing to follow. But it will just be this stuff to the 1/2 or you could write that as the square root of that stuff. However you want to do it. It'll be fine. Okay, and there we go. So just because something's all by itself doesn't mean it's not by parts. You can think of the dv part as just 1 and see where that gets you. All right, so that should be enough to get you rolling on the by parts homework, and I will talk to you next time.